will continue our discussion on gas permeability method for characterizing powder. So, as you saw, we used Darcy's relation from where we get the alpha, and using that alpha and this parameter porosity, we can get surface area. So, we will see how or the way that porosity is defined. So, this is very interesting. We use what is called as Pacman analogy. So, we are talking about porosity, and we will talk about the method which is called Pacman analogy. And if you have ever played the game of Pacman, you would like it. Though many of you from the new generation may be more aware of Pokemon Go, the game, than the Pacman. Anyhow, let's get back to, let's say this is a powder particle and it has a pore like this. So, this will be called open pore. So, what we are looking at is one particle, and this will be called a closed pore. Now, what is a closed pore and how is it different from open pore? Open pore, as you can see, is through and through the particle. So, if the gas is flowing, it will allow the gas to flow all the way through. On the contrary, the closed pore, although it comes to the surface, but it does not pass through the whole particle. So, the gas cannot pass through it. However, it is still leading to increase in the surface area, because the surface area, you can think of some hemispherical scoop cut out from the particle. So, there is a surface area increase because there is a pore over there. So, that is the difference between a closed pore and an open pore. Now, if we were to define a different true volume, you would imagine that the true volume would look like something like this. So, there is a pore over here, there is a pore over here, this is an open pore, this is a closed pore, and if we want to describe a true volume, we will take away this much volume, we will take away this volume. So, we are considering only this volume. So, volume inside this and taking away the volume taken out because of that pore. So, that will be called true volume. However, in most cases it will be difficult to estimate this volume, and therefore, what you will be estimating is what will be called a apparent volume. So, what you will actually be calculating is you will include this volume but only exclude this open pore volume, and therefore, you will be taking into account only this whole volume including this volume. So, some amount of volume has been taken, extra volume has been taken into account, and therefore, density that you will calculate will be lower than what should be for the true density. So, this will be your not true apparent volume. So, with these definition, we are now in a position to describe the term porosity that we started using last time. And in fact, we should be able to get what is called as true porosity, and you will see why we call this as true porosity. So, the true porosity can be written as, so we are looking at the relative fraction. So, it is volume of open pores plus closed pores by the bulk volume. And okay, so what will be the bulk volume over here? So, the bulk volume would be, if you had taken the whole thing including the volume of the closed pore and the volume of the open pore. So, that would have been your bulk volume. So, in schematically or graphically, what does the true porosity represent? It is a fraction of volume taken by these pores divided by the whole volume. So, that is your true porosity, and in terms of the true volume and apparent volume, we can write it like this. This will become bulk volume minus true volume divided by bulk volume, and therefore you can write it as 1 minus true volume by bulk volume, and if you divide by mass on both sides, then this becomes 1 over rho, 1 over true rho, this becomes 1 over rho bulk, and therefore you can write it as, so this rho will be in the numerator and this will become rho bulk by rho true. Now this is your true porosity, but like I said, this true porosity is also including your open pores and closed pores, but when we are using the permeability method, the gas permeability method, we know that we are not using the closed pores, and therefore the porosity that we are using in our permeability method, that will be a little bit different, and you can say that this porosity, so let me classify or refine it here, that in permeability so this will now we can say is equal to, so we can take away the closed pores, we will have only the open pores, by bulk volume, and if you rearrange it, you can see that it will become 1 minus rho bulk by what is called as rho apparent. Now what is this rho apparent? It is the density when you are calculating when you are taking closed pores also into account, density with closed pores included, and therefore this rho apparent, like I said, we are taking, this is your apparent volume, so you are taking this as the volume, so the volume amount is larger than what it should be in the true volume, and therefore the density will come out to be smaller. So this rho apparent is actually smaller than rho true, because the denominator that we are taking which is mass by volume, in over here this is larger, in over here this is smaller, and therefore this becomes a smaller quantity, and that means overall this porosity that we are calculating, if you look at the whole term over here and compare it with the true porosity, this is a larger value. So this porosity, if we were to write porosity sorry, let me refine that. So this porosity is smaller because this is of course only taking open pores and not the closed pores. So this porosity, which is from which we have used for permeability, is smaller than true porosity. So overall it gives you an understanding of what are the different kinds of pores and which are the pores being taken into account when we are talking about permeability, and which are the pores you should ideally be taking into account when we are talking about some actual surface area measurement method. So with that you can say that there is going to be some difference in the surface area that you calculate using gas permeability method and say BET method. But however, having said that, it will still give you a good you can say relation between the porosity and the surface area, and that can be related to find the surface area that we have been trying to do. So hence this method will normally underestimate. See, so what like I said that there will be difference in the porosity. Therefore, this method will normally underestimate the surface area with respect to BET method. However, you can also use this to find out that difference will be proportional to the surface area related to closed pores. So, that gives you also a tool to basically differentiate between open pores and closed pores, because one method is giving you the surface area because of both closed pores and open pores, which is BET, and the gas permeability method is giving you only the open pores, and therefore, when you compare the two results, you can also say what is the surface area that is related to closed pores. So, that is another method that we looked at, gas permeability method. So, these are most of the techniques that are used for characterizing powder. However, there are some parameters that are also very useful to characterize powder, and one of them is compressibility, because we are talking about powder processing where powder will be compressed. So, let us look at what is this compressibility. Compressibility or compactibility, meaning how much you are able to compact, measures the densification of powder under an applied load. So, it tells you how much this powder can be compressed or compacted. A simple cylinder or rectangle is filled with powder and the density is measured after compaction. Now, you know that we already are aware of the true density, but what we are measuring over here is not the true density. We will be measuring what is called as tap density or the green compact density. We are just applying a pressure and measuring how much it can compact, and you can even find it in relation with the true density. So, you can say it is 60% or 0.6 of the true density. So, that is the usual measure of the compressibility or compactibility. What is the fraction of this compressed powder with respect to true density. So, green density is the density after pressing. So, this is the after pressing you get green density, and even before you have pressed it, there will be some density that you can call as the tap density. So, you first get the tap density, which includes not only the open pores and the closed pores, but also some area, some volume in between the particles. Then you compress it and you get what is called as the green density. And then you also define a term which is called compression ratio, which expresses the volume change or density change with a standardized compaction pressure. So, you can take different powder, let us say copper and iron powders, and put standard pressure, which is 400 megapascal usually, and compress them and find out what is the change in volume or density change, relative density change, and that will be called the compressibility. And from there you can say whether copper is better suited for powder processing or iron powders are better suited for powder pressing. So, this gives you an understanding of which powder is better suited for compressing. So, this is a very important parameter. Another important parameter when we are talking about powder is agglomeration. Now, we already know that particles we are talking about are very small, they are very small in size. Now, whenever the particle sizes are very small, there will be a tendency to agglomerate. Why would there be a tendency to agglomerate? Let us see. If you are talking about powders of the size of few microns, this becomes even more important. Let us look at surface energy per unit volume. For a particle of given diameter d. Now, if the surface energy per unit area is gamma, then surface energy for a particle, a spherical particle, we are assuming you can do a similar exercise for let us say a cubical particle and find out what will be the surface energy per unit volume, how will it relate with given length. If it is a cube, let us say L is the length. In sphere, d is one of the characteristic length. So, the energy will be pi d square. This is the total surface energy for a sphere or particle of d, particle size d, and the volume is pi d cube by 6. Therefore, this comes out to be So what do you see? Surface energy per unit volume, to be precise, is inversely proportional to d. Now you know that energy will always, for a system, energy always tries to reduce, and therefore what will happen is that, how will it try to reduce this surface energy per unit volume term? By increasing d. So the system will try to have larger d on an average, so that the surface energy per unit volume is lower. And but the particle that you are producing, that is dependent, the size of the particle is dependent on the process parameters, and therefore that cannot be changed. So what the particle does is put together, or the system, not the particle, but the system does is get a lot of particles together. So the particles have the tendency to come together, and because of the reduction in surface energy, which is proportional to 6 gamma by d, they will come together, and therefore even though the small particle size was a small, very small size, but they can come together and form an agglomerate whose effective diameter will be much larger than one particle size diameter. So that is the driving force behind agglomeration, that is the reduction in the surface energy. So let us look at the slide here. So most particles are cohesive and naturally stick together, and why are they cohesive? Again, the driving force is the reduction in the surface energy. In some cases, particle clusters are difficult to separate or disperse for powder characterization. So sometimes it may happen that the particles have agglomerated and come together so much that it is not even possible to separate them out. This can lead to erroneous particle size measurement, and in that case, if you are doing the measurement, the surface energy, for example, say let us say the total surface area, that has reduced because that was the driving force, and therefore the particle size measurement, if you do, will be erroneous. So you have to be careful to ensure that there is no agglomeration when you are calculating the particle size. Capillarity forces from surface moisture causes agglomeration of particles. So you can call it capillarity forces or the reduction in the surface energy term, which leads to this reduction in the surface energy. Compression can be dispersion can be achieved in liquid. So if let us say you have achieved or you have obtained a agglomerated particle, one of the best way to disperse them is to put it in a liquid. Now in the liquid, the surface energy terms changes, and because of that you can get dispersion, and therefore you will be able to have particle size particles of their natural size, and then you can do the characterization. And that is why you remember in most of the techniques that I showed you, the particles were actually in some of the solution. When they are in some of those solutions, then they do not stick to each other and they remain separated, and then you can calculate the actual particle size. So at this point we are coming to end to the characterization of the powder particles. So I promised that we will take a look at example problem based on this, particularly to show that there is an upper size that can be characterized using the sedimentation method. You remember sedimentation method was based on Stokes law, which says that a falling particle reaches its terminal velocity, and from the terminal velocity you can calculate the distance and the time, and therefore you can say what is the approximate particle size. There was a lower limit, and that lower limit was because if the particles are too small, they will remain suspended in the fluid medium, whether it is liquid or gas, it will remain suspended, and therefore it will never reach, and therefore you cannot calculate the particle size. On the other hand, on the other extreme, there is also a upper limit to the particle size, and that is determined by the Reynolds number. Now when the particle size becomes larger and larger, the turbulence sets in, and when turbulence sets in, Reynolds number increases. That happens at approximately the Reynolds number of 0.2. So let us say the Reynolds number is given as 0.2. You are given to find the maximum particle size for particles of a material whose rho m is given, and it is settling in a fluid. So the fluid density, viscosity is given, fluid density is also given, and then you have to do the same calculation for another fluid. The difference being that this time the viscosity is very different, and also the density is very different. So we will see how these parameters will make a difference to the maximum particle size. So let us try to solve this problem. So remember what we are trying to do. We are trying to get maximum particle size that can be characterized using sedimentation. Now, here we need another equation that we have not discussed in our regular class, and that is the relation of Reynolds number with velocity, diameter of the particle, fluid density and its viscosity. Now, we said that Reynolds number is given as 0.2 or it is that Reynolds number where turbulence sets in and we cannot apply the Stokes law. So we are given that this is 0.2 and this is proportional to d. So, in general you would want the particle size d to be smaller than this critical size. So, let us say we are finding that critical size and the critical and the diameter of the real particles should be smaller than this. So, our d critical should be will be equal to Rn times V rho f, and we also have the diameter from the other equation where we had where we used the Stokes law. So, we want to say what will be the d critical that we obtain from here and put that value into Stokes law. So, for that what we will do is we will calculate the terminal velocity which is over here. So, let us say this is happening at some terminal velocity Vt for this critical diameter d. So, the Vt will equate V, that critical value of V that is obtained from Rn, and the critical value of V, not the critical but the terminal velocity that we obtained from Stokes law. So, we put them together and we get okay. So, let us understand what we are trying to say here. For a particular size, critical size diameter d, there is this velocity v. So, the velocity v, this is the velocity Vt. Now, this velocity Vt is the largest that the particle should have, otherwise it will start to get into the turbulent mode. And we are also saying that this is the same velocity or the particle size is such that we are getting the terminal velocity for this particular particle. Therefore, the velocity, terminal velocity is same, and therefore, we have equated it over here, and from here we will get d cube sorry, this is not 1 by 3 yet. So, this is d cube and this is equal to this, and therefore, if you want to find d, you will take away 3 from here and put 1 over 3 over here. So, this will give you that d critical, that critical diameter. If your size is less than this, then velocity Vt will remain below this terminal, this velocity will remain below a velocity value at which turbulence will not set in, and even though it reaches terminal velocity which most particles will reach. So, you would be able to use Stokes law. So, we are equating the velocity v over here, and from there we are getting the d critical. If you put in these values, you would see that this comes out to be 27 micrometer. So, you cannot put particles or you cannot characterize particles which have values larger than 27 micrometer. And not only that, we also have you remember from our earlier discussion when we were discussing about sedimentation, that there is a lower limit, and so there is D should be less than 27, or not 27, let me say some D upper limit, and it should be greater than some D lower limit for sedimentation. Having said that, now second part of the question is to find out the D critical when we change the value of the liquid. So, if you see, compare the values, let us get to the slide to see what is the density comparison. So, the first fluid has density of 1.2 kg per meter cube, and compare with the other fluid which is water, the density is 1000 kg per meter cube. So, it is 3 orders of magnitude larger. On the other hand, viscosity is very, very low for the first fluid, it is of the order of 1.8 into 10 to the power minus 5, and for the other liquid it is, or which is water, for that the viscosity is 1 into 10 to the power minus 3. So, this is again 2 orders of magnitude larger. So, viscosity is larger and density is larger. How does that make a difference? And when you solve this, what you would see is that this would come out to 17 micrometer, and this will increase to 27 micrometer. So, basically when you go from lower density liquid to higher density liquid, you are able to increase the upper limit. So, let us write it down what has happened when you use a higher density implies larger upper limit. So, just one correction over here, we will get 17 micrometer for the first fluid and 27 micrometer for the second fluid, which is water. So, when you increase the density, so this was 1000 kg per meter cube fluid, which is water, and this was just 1.2 kg per meter cube. So, when you increase the density, our particle size limit has increased. But what is again interesting is that the magnitude of increase here is very small. You see, we have increased the density 3 orders of magnitude, viscosity 2 orders of magnitude, but the size has increased by only 50%. So, that is a very small increase, although it will be very significant because your lower limit may probably be of the order of 1 or 2 microns. So, we are talking about 2 to 17, and then we go from 2 to 27. So, you have to use a proper liquid depending on what is the particle size and with proper viscosity to be able to characterize powders. So, this is the example that gives us an understanding or feel of why there is a lower limit as well as an upper limit when we are using sedimentation based on Stokes law. So, that is the end of our powder characterization. In the next lecture, we will start with the next topic, which is powder fabrication or powder manufacturing. So, we will be discussing about different techniques which are used for making the powders. So, thank you and see you in next class.